So last time we were discussing about variation of mass with velocity and how Einstein proved that the mass of a body can change if the body is in motion. In contrast to when we consider mass to be constant when we were dealing with Newtonian mechanics. So if mass is not constant, mass varies with velocity, then the associated things like momentum, energy, force, these were the basic things we dealt with when we were doing Newton's mechanics or Newtonian mechanics. And these all things are needed to be modified as per according to relativistic corrections. Okay, but before doing that, we will focus some time on what is momentum. And the good thing about it is how momentum is conserved. The actual formula of momentum is mass into velocity, and this remains conserved. So we have a few slides over here. So this is, so let it repeat again. We have a bomb, which is, let's say, of mass m, and it is not moving, so velocity is 0. If its velocity is 0, then definitely what we have to consider is that its momentum is also 0. But when it's burst, some of the portion goes on the right side and some of the portion goes on the left side. But definitely then also, if let's say m2 is going on right side with velocity v2 and m1 is going on left side with velocity v1, then m1 plus m2 m1 m2 and m1 v1 plus m2 v2 should be equals to 0. That is conservation of momentum. But the thing's not end here. If you are still not getting what conservation of momentum is, you can understand from this example. Ball 2 was at rest, then ball 1 came running, it was having momentum, and this momentum was transferred onto ball 2. और जो बॉल 1 है, परफेक्ट collision की वजह से वो रुक जाती है और अपना सारा momentum 2 को ट्रांसफर कर देती है. This is another example. Yet another example is Newton's cradle, जिसमें we have given displacement to a ball और आप देखें that momentum is transferred to the endpoint balls like this. You can also have a few funny examples like this brother and sister, and they are playing. You can see that जिसका mass कम है उसकी velocity ज़्यादा हो गई है और जिसका mass ज़्यादा है उसकी velocity कम है, because we have to conserve m1 v1 and m2 v2. Another example is of aerodynamics और airplane motion. तो केवल यही नहीं कि हमने एक बॉल ली या you have marbles और उस पे momentum या conservation of momentum आप apply कर रहे हैं. It is also applied to fields like aerodynamics, जहाँ the air which is being propelled outside or towards the back side, उतना ही thrust the airplane will gain in front direction. Okay, so this diagram is for that. Yet we can have some other examples. So if you still have doubt whether momentum is conserved or not, you have to watch this one. So he's having a rocket launcher, and because the pressure is towards left side, or the bottle is moving towards left side, the water is leaving from the right side. Yet another example is this. So you have to be very careful when you are firing something. And we have this example as well. So they are not to doubt physics when you have such things with you. So yesterday we analyzed that when we were having body A or ball A and another ball B, then if you look from rest frame and say something about body B, then you got an expression which was something like this. So we have got that mass can be related with the proper mass m naught as m is equals to m naught 1 minus v square upon c square, where v is the velocity of the moving frame. Fine. So if we have things going like this, then we should write this as m is equals to gamma m naught. When I'm saying m is equals to gamma m naught, so what I've done is I have written gamma is equals to 1 upon under root 1 minus v square upon c square. और जो मोमेंटम होता है उसकी इक्वेशन क्या क्या लिखते हैं आप? द मोमेंटम इज गिवन बाय, बिकॉज इट इज अ वेक्टर क्वांटिटी, you can write this momentum as mv. Okay, momentum is equals to mass into velocity. But now this mass is which type of mass, your proper mass or the relativistic mass? So you have to write, if you want to write this in terms of proper mass, you can simply write that P is equals to gamma m naught v. Fine. And if you will go in this way, then things will change a little bit. How? Let me just show that to you. So if you have, let's say, classical momentum, and so this graph shows over here, you can see that if you have classical momentum, then having velocity 0, m into 0 will make it what? If you have velocity 0, m into 0 is momentum also 0. And on increasing the velocity, your momentum will increase. So here on the x-axis, instead of writing just velocity, what we have taken is comparative या ratio of velocity to the ratio of velocity of light, v by c ले लिया है. So we know that maximum velocity a body can attain is c. So maximum ratio of velocity can be 1. Fine. So अगर हम classical momentum देखें, जिसमें what we were having is that we assume that it is only m into the velocity. So if you go by that relation, if a body is having velocity c, तो उसका momentum होना चाहिए mc. यहाँ से देखें, it should be equals to mc. So if the body is moving with velocity c, इसका मतलब v by c की वैल्यू हो जाए 1, तो उसका momentum classical न्यूटोनियन मैकेनिक्स से होना चाहिए था mc के बराबर. But क्योंकि हमने relativistic correction लगाया, then instead of treating momentum to be just m into the velocity, we have to take it as gamma into m into the velocity. And आप देखें, if velocity becomes equal to the velocity of light, तो gamma की वजह से this gamma will turn to infinity. So the momentum will also become infinity. And momentum is a physical quantity by the virtue of which you feel mass, you feel impact, you feel force. Fine. So that is how linear momentum varies in relativistic mechanics. It's not just mass into velocity, it's mass into velocity into gamma as well. Fine. Where definitely over here in this diagram, m is to be considered as the proper mass. Fine. So you have to consider m as proper mass over here. That's it. That's first correction. Now let us move on to few different things. We call this as mass energy equivalence or energy mass relation. Fine. So how do you define Newton's second law of motion? Well, if we write only the mathematical statement, then force is defined as the rate of change of linear momentum. If it's a vector quantity, we can consider P to be a vector quantity as well. Okay, so we consider force to be defined as rate of change of linear momentum, and also we know that linear momentum, अभी हम classically देख रहे हैं, should be equals to mv. Fine. So we can write that force is nothing but equals to dp by dt, या हम लिख सकते हैं d by dt of mv. Fine. And how do we define work? So we have to, from force we now have to come to what is called as energy. तो force से हम work पे आते हैं. We define force into displacement f dot s as work. या फिर अगर मैं बहुत छोटे डिस्प्लेसमेंट की बात कर रहा हूँ, यानी आई एम जस्ट टॉकिंग अबाउट dw, so I can write that force dot ds or a small displacement. Right? तो अब ये दोनों चीजें एक साथ रख देते हैं, यहाँ से जो हमने फोर्स की इक्वेशन निकाली एंड ds, so you can write this as d by dt of mv dot ds. Fine. और यहाँ what we will use that we consider that this small d is just like a differential operator, so I can also write this as dmv dot ds upon dt. तो ये एक और v बन गया हमारे पास. तो it has now become ds upon dt is velocity. Okay, v differential of mv, v into differential of mv. I've got it like this. And because this was small work, I can also relate it as it was nothing but small kinetic energy, a small energy. Fine. So we got an equation that you can write small kinetic energy as equals to v derivative dmv. Okay. But now, as we have seen that mass is also not constant, velocity is also not constant. Both can vary. Okay. So in that way, what we can write is that dek can be written as v. अब यहाँ partial derivative हम लगाएंगे, ठीक है, या product rule. You can keep m constant and take derivative of v, plus you can take v constant and derivative of m. So in a way, what we have got as equation is dek will be nothing but equals to v square dm, if we consider that mass also varies, plus mv dv, v square dm plus mv dv. So this is the equation which we have got from simple Newton's mechanics which we were following. But in between we assume that mass is also not constant, mass can also vary with velocity. Okay. So this is equation 1. We will need this equation in order to prove a very famous relationship, but as of now you just take this as an intermediate step of what we are going to do in coming moments. Now after that, so we have got this equation. Consider what we already derived yesterday. M is equals to m naught under root 1 minus v square upon c square. Right? Let us take square both side, or squaring both side. What you will get is this. You will get m square is equals to m naught square upon under root 1 minus v square upon c square. Further moving from here, what you will get is m square 1 minus v square upon c square can be written as m naught square. Okay. Yet moving ahead, you will have m naught square c square minus v square is equals to m naught square c square. ये c square यहाँ common लिया and it has gone there. So what we got is this. You have m square c square is equals to m naught square c square plus m square v square. Okay. So एक रिलेशनशिप हमारे पास यहाँ से आएगी. अब यहाँ in this equation what we'll do is we will take derivative या partial derivative with respect to m and v, because these two are variables now. So in this equation, what equation we have got? We have got this equation which is m square c square is equals to m naught square c square plus m square v square. So if you consider this equation, यहाँ से देखें, अगर हम partial derivative लें with respect to v and m, what you'll get is ये c square तो constant हो जाएगा, इसका हो जाएगा derivative 2m dm into c square is equals to, अब इस चीज का डेरिवेटिव, बिकॉज m नॉट तो कांस्टेंट है और c भी कांस्टेंट है, तो डेरिवेटिव ऑफ दिस इज 0 प्लस यहाँ दो चीजें अलग अलग हैं और दोनों का अलग अलग डेरिवेटिव आएगा. अगर आप m के रिस्पेक्ट में लेंगे तो इट विल बिकम 2mv स्क्वायर dm. ओके, 2mv स्क्वायर dm, और अगर v के रिस्पेक्ट में लेंगे तो इट विल बी 2m स्क्वायर v dv. फाइन. तो हमने केवल पार्शियल डेरिवेटिव लिया है with respect to m and v, and we have got this equation. ठीक है. If you solve or just eliminate a few terms, what you'll be left with is this: c square dm will be equals to, so हम 2m कैंसिल कर रहे हैं यहाँ से, 2m will go from here, you will be having v square dm प्लस यहाँ से बचा ये 2m कैंसिल हो जाएगा, mv dv। एंड थोड़ी देर पहले हमने एक इक्वेशन निकाली थी दैट v स्क्वायर dm प्लस mv dv इज नथिंग बट इक्वल्स टू स्मॉल काइनेटिक एनर्जी। तो हमें ये पता चला कि ये जो टर्म है वो दरअसल dek के बराबर है। सो वी हैव गॉट दिस दैट जो छोटी काइनेटिक एनर्जी बदलेगी किसी भी चीज की वो c स्क्वायर dm के बराबर होगी। फाइन। सो इफ यू हैव दैट स्मॉल चेंज इन काइनेटिक एनर्जी ek इज गिवन बाय c स्क्वायर स्मॉल चेंज इन मास, ठीक है। तो अगर हम इंटीग्रेट करें बोथ साइड, सो इफ आई इंटीग्रेट बोथ साइड, तो यहाँ मुझे 0 से लेकर ई के तक वैल्यू मिलेगी। यहाँ कम से कम मास m नॉट हो सकता है और ज़्यादा से ज़्यादा मास m हो सकता है एट वेलोसिटी v, ठीक है। सो वी विल गेट अ रिलेशनशिप ऑन इंटीग्रेटिंग बोथ साइड, व्हाट वी विल गेट इज, या तो हो जाएगा ई के माइनस 0, तो ई के हो जाएगा, एंड ओवर हेयर व्हाट वी विल गेट इज एम सी स्क्वायर माइनस एम नॉट सी स्क्वायर। ओके, तो ई के क्या है, ई के इज काइनेटिक एनर्जी। काइनेटिक एनर्जी इज इक्वल्स टू एम सी स्क्वायर माइनस एम नॉट सी स्क्वायर। अब यहाँ कई सारे टर्म्स हमें समझ में आएंगे दैट व्हाट यू हैव इज ई के प्लस एम नॉट सी स्क्वायर is equals to mc square. Okay, and this is a very famous relationship. We call it as mass energy relation. We will also call it as E is equals to mc square. वही वाली रिलेशन है। वहां पे जो E हम बोलते हैं वो उस E के अंदर ये दो टर्म्स आते हैं। शायद आपने पहले नहीं पढ़ा हो लेकिन अब पढ़ लीजिए। जो E लिखा जाता है वी राइट E इज इक्वल्स टू mc स्क्वायर। उस सिंगल E में दो अलग अलग तरीके के कंपोनेंट्स होते हैं। तो E I can write as the total energy E is equals to the kinetic energy plus the rest mass energy m naught c square। तो ये जो एनर्जी बोल रहा हूँ मैं, इसे मैं एनर्जी बोल रहा हूँ। अब आप सुने गौर से, मैं इसे एनर्जी बोल रहा था। सो दिस इज कॉल्ड एज रेस्ट मास एनर्जी। और जो ई के था इसको हमने पहले भी बताया, दिस ई के वॉज काइनेटिक एनर्जी। सो द टोटल एनर्जी विच इज गिवन बाय एम सी स्क्वायर is sum of the kinetic energy Ek plus the rest mass energy. So we write E is equals to mc square. तो total energy kinetic energy plus rest mass energy का sum है। तो ये बॉक्स कर लीजिए, ठीक है। You can write E is equals to mc square. You can also write kinetic energy plus m naught c square is equals to mc square. Both are one and the same thing, ठीक है। We will see or discuss a few examples. जैसे आपने अभी इलेक्ट्रोमैग्नेटिक्स नहीं पढ़ी है, बट एक स्पेशल तरीके के रेडिएशन होते हैं जिन्हें गामा रेज बोला जाता है, गामा रेज। तो जैसे मान लीजिए एक गामा रे का फोटोन है, तो इलेक्ट्रोमैग्नेटिक रेडिएशन में यू हैव डिफरेंट फोटॉन्स। यू हैव अ गामा रे फोटोन एंड दिस फोटोन इज ट्रैवलिंग बाय, एंड दिस गामा रे फोटोन एक्चुअली passes nearby a nucleus of an atom. किसी न्यूक्लियस के पास से जाता है। दिस एग्जिस्टेंस ऑफ दिस गामा रे, जो कि केवल एनर्जी पैकेट है, एक्चुअली सीज टू एग्जिस्ट, यानी वो गामा रे फोटोन खत्म हो जाता है और दो पार्टिकल्स जो कि मास है अपने आप में, एक पॉजिट्रॉन और एक इलेक्ट्रॉन रिलीज हो जाते हैं। तो एनर्जी के बदले पार्टिकल दे दो। आर यू गेटिंग इट? एनर्जी के बदले पार्टिकल दे दो। या फिर आपने एक इलेक्ट्रॉन लिया और एक पॉजिट्रॉन लिया, उसका एक एटम बनाने की कोशिश की, दैट दे आर रिवॉल्विंग अराउंड ईच अदर। थोड़ी देर में दिस इलेक्ट्रॉन एंड दिस पॉजिट्रॉन विल एनिहिलेट ईच अदर। एनिहिलेट मतलब खा जाएंगे एक दूसरे को। एंड व्हेन दे विल मर्ज और एनिहिलेट, ना तो इलेक्ट्रॉन बचेगा ना ही पॉजिट्रॉन बचेगा और गामा रे की एनर्जी निकल जाएगी और वहां पे उन इलेक्ट्रॉन पॉजिट्रॉन का एग्जिस्टेंस समाप्त। सो दीज आर the interconversions or interrelation between how you can convert mass from energy and energy from mass. Fine. Well, that is a matter of nuclear scientists to deal with. We are only doing relativistic mechanics. After doing the mass energy relationship, next on our hit list is relationship between energy and momentum. So अब energy और momentum में भी अपने आप में एक relation होती है, that we have to define. So this is energy momentum relationship. एक mass energy relationship देखी, अब हम देख रहे हैं energy momentum. Okay, momentum, as far as you know, it is nothing but P is equals to mv. But now this m is to be written in some different way, that you have to write m as m naught into v upon under root 1 minus v square upon c square. This is the momentum and how you have to write it. Fine. जो टोटल एनर्जी होती है किसी बॉडी की, अभी थोड़ी देर पहले देखा, वो लिखी जाती है mc स्क्वायर से. तो इन अ वे यू कैन राइट टोटल एनर्जी इज इक्वल्स टू m नॉट c स्क्वायर और डिवाइडेड बाय, बिल्कुल ठीक, 1 minus v square upon c square, because you can write this m as this. Fine. Now you take square on equation 1 and square on equation 2 as well. दोनों साइड स्क्वायर लीजिए. So when you will take square of p square, so यहाँ से मैं लिख देता हूँ that p square will become nothing but equals to m naught square v square upon 1 minus v square upon c square. और अगर आप e square देखें तो यहाँ your e square will become m naught square c square upon 1 minus v square upon c square. Fine. You will get things like this. M naught square c square 1 minus v square upon c square. Now, what I want is you find out what will be this equation. E square minus p square c square. तो इस इक्वेशन में c square का मल्टीप्लाई करना है और इसे e square से माइनस कर देना है. ठीक है. So what we will get is we are just getting confused. So if this is m naught square, then this should have been m naught square c की power 4. Instead of just writing c square, it should be c की power 4. So please make that correction. And now because यहाँ मेरे पास केवल v square टर्म है, यानी वेलोसिटी स्क्वायर है, तो मैं c square से मल्टीप्लाई करके I'm making the dimension same. If I have done that, so you will get to know that यहाँ मिलेगा मुझे m naught square c की power 4 divided by 1 minus v square upon c square minus m naught square v square और साथ में कहा p into p square c square का मल्टीप्लाई करना है, तो you will have also have c square 1 minus v square upon c square like this. Fine. अब इन दो इक्वेशंस को आप लिख सकते हैं कुछ इस तरीके से. You have 1 upon 1 minus v square upon c square, ये कॉमन लिया आपने, और दोनों साइड से m naught square c square कॉमन ले लिया. यहाँ से m naught square c square कॉमन लिया, यहाँ से m naught square c square कॉमन लिया, तो आपके पास जो बचेगा that will be c square minus v square. Okay, you are left with only c square minus v square. अब इस इक्वेशन से so we have got what? E square minus p square c square is equals to m naught square c square upon 1 minus v square upon c square, और साथ ही हमारे पास है c square minus v square. अब इस इक्वेशन में यहाँ से if I take c square common, तो c square इससे मल्टीप्लाई होकर c की पावर 4 हो जाएगा. So we will have e square minus p square c square is equals to m naught square c की पावर 4 1 minus v square upon c square and divided में हमारे पास है 1 minus v square upon c square. This will get cancelled. So energy momentum relationship जो आई, that is this, that energy square is equals to m naught square c raised to the power 4 plus p square c square. Okay, so you mark this. So एक relation आपने पढ़ी थी E is equals to mc square, which is just energy mass relationship. This is E square is equals to m naught square c की power 4 plus p square c square. This is energy momentum relationship. Fine. So this is equation number 2, or the second important equation for today's class. Now we'll move on to the last important equation, which is rather very easy, about expression of kinetic energy or relativistic kinetic energy. So you know relativistic momentum, relativistic mass, relativistic energy. Now we are going to focus only on relativistic kinetic energy. In relativistic kinetic energy, अभी थोड़ी देर पहले we were discussing that small ek is given by c square dm, and when we integrated both sides, we could get that ek is equals to m naught c square, sorry, I should write mc square minus m naught c square, where m naught is the proper mass. So we got mc square minus m naught c square, we got something like that. Fine. Now you can simply write m is equals to m naught upon under root 1 minus v square upon c square. So you can write kinetic energy is equals to m naught c square upon under root 1 minus v square upon c square minus m naught c square. So that's it. I mean, that's done. So you have m naught c square, the rest mass energy, we call this as rest mass energy, 1 upon under root 1 minus v upon c square, v square upon c square minus 1. People also call this whole term as gamma. So you can simply write your ek or kinetic energy is given by the rest mass energy into gamma minus 1, where gamma is 1 upon under root 1 minus v square upon c square. Okay, so the kinetic energy is equals to m naught c square, which is the rest mass energy, into gamma minus 1. So this is the derivation of third relationship. We call it as relativistic kinetic energy. Fine. So if suppose that you are given, let me just take up a question, that the kinetic energy, this is, you can take as an example, that kinetic energy of a particle is 3 times its rest mass energy. And what you have to do, you have to find out what is velocity. So it's given that ek is 3 times, what is the rest mass energy? Uski equation hoti hai m naught c square. So it is given that ek is equals to m naught c square, but you also know that ek is given by m naught c square gamma minus 1. That's how we write it. Fine. तो हम यही करते हैं, दोनों साइड इक्वेट कर देते हैं. You have got 3 m naught c square is equals to m naught c square gamma minus m naught c square. So actually we got 4 m naught c square is equals to gamma m naught c square. And यहाँ से क्या हुआ, m naught c square cancel हो गए. So you are left with what? You are left with 4 is equals to gamma. And gamma क्या था? Gamma was equals to 1 upon under root of 1 minus v square upon c square. So we got 4 is equals to 1 upon under root of 1 minus v square upon c square. यहाँ से क्या करें, square both side, you will get 16 is equals to 1 upon 1 minus v square upon c square. So you can write this as what? 1 minus v square upon c square is equals to 1 upon 16. Fine. And now you can write this as 1 minus 1 upon 16 is equals to v square upon c square. And from here you can write simply that 15 upon 16 is equals to v square upon c square. So यहाँ से what you can write is, it gives you the answer that actually your v will be equals to under root of 15 by 16 into c. That's it. You got the velocity. So the velocity, if you solve this, this should be 1 by 4 and root 15. You can please check whether your answer is coming something like this: 2.904 into 10 to the power 8 meter per second. I have already solved it, so you can check if you're getting the same answer or not. That's it for today's class. We will see a few more questions on, or I should say, numerical questions on relativistic mechanics, and that covers your unit 1. Thank you so much, all of you.